now let's move to the second speaker, second paper, NG Song. NG is now an engineer at Alibaba Cloud. As a researcher in cloud network, he received his PhD from Beijing University of Post and Telecommunications. And his research interests include cloud network protocols and architectures and the model context protocol. Today, he will be talking about a system called Nezha, a SmartNIC-based solution for virtual switch load sharing. So, NG, it's your time.
Thank you. Hi, everybody. I'm Ng Song, coming from Alibaba Cloud. Now I'm going to introduce one of our research work titled Nezha, SmartNIC-based virtual switch load sharing. Virtual switches are important for cloud vendors. In data centers, vSwitches enable network communication under tenant isolation and enforces user-defined rules such as routing, metering, and NAT. SmartNIC-based vSwitches are widely deployed in data centers to provide hardware-accelerated networking for virtual machines, containers, and serverless services. After deploying SmartNICs for over 8 years, we have observed the simultaneous vSwitch resource shortage and waste. We discovered that the demand on some network capabilities for high-load tenant VMs could not be met, as also reported by Azure. As shown in Figure 1, we found that these high CPS VMs cause severe overload on their servers' SmartNICs, with CPU utilization over 95% in all cases. Meanwhile, these high CPS VMs are lightly loaded, with 90% of them having CPU utilization below 60%. In the same time, we observed that only a few SmartNICs exhaust their CPU and memory resources, while most have very low resource utilization. The average CPU and memory utilization of vSwitches in a region were about 5% and 1.5%, while P99.99 utilization reached 90% and 96%. Based on our analysis, the root cause of resource waste is most service usage come from a small number of heavy users. As shown in the table, the P50 usage of CPS concurrent flows and the number of vNICs are below 1% of the P99.99. Then we will introduce the current vSwitch packet processing logic to better understand the root causes of resource shortage. As shown in the figure, the first task is maintaining vNIC level rule tables, and then look up rule tables to generate preactions for first packet, and cache preactions as flows for fast processing of subsequent packets. It also needs to store the session states for stateful network functions. And finally, get the final action with preaction and state. There are 3 important components in the workflow: the rule table, the preaction, and the states. The rule table, such as the routing, metering, ACLs. The preaction is forward or job or header rewrite, and the states, including the TCP, FSM, flow level statistics, and so on. The rule table and preaction are stateless. And then we will analyze root causes of resource shortage. Each flow's first packet trigger logic execution on the vSwitch slow path, involving queries to multiple route tables and consuming substantial CPU resources. Therefore, the new connections per second, that is the CPS, is limited by CPU. Besides, since the memory available for storing flow entries and route tables is limited, both the number of concurrent flows and vNICs are limited by memory. There are some potential solutions. First solutions are rolling out the high-capacity SmartNICs, but upgrading all servers is not cost-effective. Upgrading select servers requires the migration of high-demand VMs to those few servers, resulting in connection interruptions. As shown in Figure 1, VM migration downtime grows with the vCPU cores and memory. While leveraging hosted resources is another method, it faces the following issues. First, it's not suitable for bare metal environments. Second, it consumes significant system resources, thereby reducing the tenant sellable resources. Moreover, software vSwitches inherently suffer from low performance. And finally, there are potential isolation risks. Some solutions use remote resource pool for offloading. But remote state maintenance faces challenge in synchronizing states across replica nodes for failure tolerance and load balancing. Besides, inline state replication limits the achievable CPS to only half of the total capacity, and requires the coordination between replica to implement VM-level rate limiting. Another problem is introducing additional hardware, which leads to upfront and ongoing CAPEX and OPEX. The performance is tied to the vendor-specific chips. Based on the above analysis, no solution meets all of the features we need. In light of these issues, we follow the principle of reuse before adding resources and propose Nezha, which leverage idle SmartNICs on other servers as a resource pool for high-demand vNICs. That's a simple idea. To avoid the complex state synchronization across the involved SmartNICs, we decide decouple and offload the state from the stateless rule table and flow table. There are some components in this system. The first is the vNIC backend, which manages the states locally, and while the remote node is called vNIC backend, which manages the rule table and cached flows remotely. Since the two inputs for packet processing are stored separately in front end and back end, we leverage packet to carry information from one end to the other. We configure, in this workflow, we only introduce one extra hub for both egress and ingress packets. For failover and load balance, the front end and the back end are in a many-to-one mapping, and leverage the hash-based load balancing and active-active failover, just because the front end are stateless. Then we will introduce the workflow of initialization and updating of three important components in our system. The rule table is initialized and updated by the controller according to the tenant intent, while the cached flows is generated through a rule table lookup when a flow cache miss occurs. But interestingly, the states are initialized and updated in different ways. Some rely on the results of the rule table lookup, that is the rule table involved case, while others utilize the information embedded in the packets, that is the rule table not involved case. There are two examples. There are two examples. For the rule table involved case, the flow level statics needs the state to record the statistics, which is obtained by querying the statistic policy table in the front end. For the rule table not involved case, is a stateful decap. Its state is the first packet direction, which can be decided by read the packet. There are few issues to be addressed when deploying Nezha. To seamlessly offload the vNIC to remote, we follow these steps. First, we need to select offload vNIC from lots of vNICs. We detect offloaded vSwitch by checking the CPU and memory usage by the controller. After that, we order the vNICs by CPU and memory usage in descending order. The second step is selecting 4 idle vSwitches which have similar performance affecting attributes, including the link bandwidth usage, the distance in class topology, and so on. Then offload the vNIC one by one until the utilization falls below a safe level. To ensure the proper packet processing during offloading, we maintain information in both remote and local, which we call the dual running stage. The dual running stage completes within 2000 milliseconds in our cloud, just as shown in the figure. To prevent sudden traffic surges from offloading vSwitches, we monitor the resource utilization of front-end hosting vSwitches. When the alert is triggered by excessive resource usage from offloading, Nezha increases the number of FEs for load balanced vNIC offloading traffic, which is called scaling out. If the alert is triggered by excessive resource usage from local traffic, Nezha scales in front ends by removing all front ends on this vSwitch to prioritize resources for local traffic. Offloading introduces extra latency, so the threshold for scaling out and in is lower than that for offloading. Then we will go to the performance. We first show the performance in test bed. As shown in the right figure, the CPS stays around 3.3 times when the number of front ends exceeds 4, and the bottleneck is in the VM. The number of concurrent flows stays around 3.8 times when the number of front ends exceeds 4, and the bottleneck is in the backend. The number of vNICs is proportional to the number of front ends, which we don't observe a bottleneck. As shown in the right figure, the growth of CPS doesn't always correlate with the number of vCPU cores, and we think the VM kernel is the processing bottleneck. Then we will show the performance on cloud. As shown in the table, since different middle boxes have different resource demands, their performance gains also differ, such as the NIC gateway improves the number of concurrent flows to 50 times, while the load balancer just improves 5 times. These 3 figures shows the overloading times before and after deploying Nezha. We mitigate over 99.9% of vSwitch overloads caused by high demands on CPS and the number of concurrent flows. And we prevent overloads due to excessive number of vNICs completely. This table shows the completion time for activating offloading. The average and P99 completion times are approximately 1 second and 2 seconds. This indicates that as long as the vSwitch can manage the current load within 2 seconds, Nezha can help prevent overloading the vSwitch in most cases. Table 2 depicts the deployment costs of Selfish and Nezha. Selfish leveraged Tofino to build our cloud gateway. It introduced a new hardware, which requires lots of tasks, such as chip selection, design, prototype testing, security assessment, and performance optimization. A service which introduced 100% mass, while Nezha reused idle SmartNICs and has 0 hardware development cost. As introduced new hardware requires completely functionality development for a new device, Selfish software development cost is about 48% mass. Nezha utilizes existing SmartNICs and modifies less than 5% of the existing vSwitch code, resulting in only 15% mass for software development. The slight modification to the vSwitch code allows Nezha to fully reuse the existing vSwitch team, so the extra human effort for iteration is 0, but the Selfish needs 20% mass to do that. Deploying Selfish to a new region or scaling out requiring selecting a data center, finding suitable racks, and setting up equipments, which may take 1 to 3 months. Nezha only needs to launch the new version to the vSwitches, which with a cluster level release, typically taking 1 to 7 days. In this paper, we also show the experience of deploying Nezha in Alibaba Cloud, including the new capabilities introduced by Nezha, such as the flexible new feature release, cost-effective fault recovery, and efficient VM level migration, and also the how to support for massive vNICs on VMs, how to handle load imbalance in Nezha, and how to increase the number of concurrent flows in Nezha. And also the deployment issues and the response when deploying Nezha, which can be found in this paper. then we will make a conclusion. In this paper, we propose Nezha, an architecture that leverages idle SmartNICs as a remote resource pool to offload high-demand vNICs without introducing additional hardware. The reuse strategy allows us to avoid extra deployment costs associated with purchasing new devices, wiring, and software development, as well as additional human efforts for future iterations. With partial decoupling design, Nezha achieves load balancing and fault tolerance across the nodes in the resource pool using only 5-tuple hashing, without the need for complex mechanisms such as symmetric and consistent hashing. That's all. Any valuable questions will be appreciated. Thank you.
Very nice talk. Time for questions.
Okay, thanks for a great talk. Junyi from Huawei Canada. So I have one question. So do you require the routing table, the overlay routing table modification in your work? Because like, for example, if there is a flow which is targeted for node A, and then this flow is selected to be offloaded the processing in node B. So would you first, node A receives the flow, forward to node B for the processing, and then transmit back to node A, or you will change the routing table to direct forward that flow to node B?
Oh, that's a good question. Let me show. Just as shown in the figure, we configure the backend location config on the front end and configure the front end location config in the backend. They can know where is the backend and where is the front end. But if the config is not installed or the routing table is not installed to the source switches, the packet may send it to the directly send it to the backend, not the front end. Yeah, for this case, we configure. We do not delete the route tables, the cache flows, the states instantly. We will make a dual running stage. The route tables, cache flows, and states are also maintained in the backend for 200 milliseconds. So the packet, if the packet is routed to the backend, it will be processed at the backend. If the packet is routed to the front end, it will be processed in the front end. There is not routed from backend to front end.
Okay, I see. Okay, thank you.
Hi, great talk. So my question is, I was curious about the reliability aspects. So for heavy hitting vNICs, for example, which are now using...
Please speak louder.
Yeah, sure, okay. I was curious about the reliability aspects, especially for the heavy hitting vNICs, which are now using multiple physical SmartNICs, right? So is the overall reliability of the system from the vNIC perspective lower? Have you observed any, because SmartNICs in general have their own reliability issues, both due to hardware, software, etc. So I was just curious about your thoughts on how does the system, can it increase reliability as well? Because as defined, it looks like it'll actually decrease the reliability from a vNIC perspective. Yeah.
Okay, thank you. That's a good question. Introducing, decouple the logic to front and back end indeed incur the challenges in reliability. Yeah, but we do active failover. If one of the front end is down, the traffic will be routed to the other 3 front ends. Because the front ends are stateless, all of them can process the packets, process the packet. So the failover we think is okay, but it indeed take we think is 2 seconds to failover in our system. Yeah, we don't show in the PPT, but in the paper you can see it.
Okay, thank you.
Any more questions? So it seems that you have quite a few experience. Is this a real deployment in Alibaba
yeah.
Cloud?
Yeah,
How long it has been deployed?
it's just 1 year.
1 year. Okay, good. Okay, let's thank the speaker again.